Good morning, everybody. I'm going to finish up the material for the quiz today. I just have one more small little issue to talk about and then move on to our next topic, which is going to be nuclear magnetic resonance spectroscopy, NMR spectroscopy. And we'll spend a couple of lectures talking about that. Okay, so last little topic for stereochemistry is a short little discussion about chirality in the laboratory. So we talked a lot about chirality and RNS and all of this other stuff. And so I just want to finish up talking about this topic by discussing how it is that chirality is measured or detected in a laboratory setting. And the main tool here is the fact that a chiral molecule rotates the plane of polarized light. And this phenomenon is called optical activity. And a sample that rotates the plane of polarized light is said to be optically active. Okay, so let's look at the experimental setup. Okay, so in this optical activity experiment, the device, the instrument that is used is called a polarimeter, and here's a schematic of a polarimeter. So you have a lamp, and you have a polarizer, and then you have a sample tube. This is usually a solution in which a chiral molecule is dissolved. Okay, so now you turn on the light, and what happens is that the photons that are emitted from the light pass through the polarizer, and the polarizer only admits, or it only allows to pass through those photons whose electric vector is oscillating in a given direction. The polarizer absorbs all of the photons whose electric vector are not oscillating in a predetermined direction that is determined by the polarizer. Anyway, the photons enter the solution where the chiral molecule is, and the chiral molecule will rotate the plane of the polarized light. So that's pictured over here on the right-hand side of this image, where the plane polarized light entered at a certain angle, and the chiral molecule rotates the plane of polarized light by a certain angle, which is called alpha. And on this slide, that subscripted D means it's the D line of sodium. That is the source that is used as the lamp. Okay, so that's the basic principle here of the polarimeter. It's that a chiral molecule rotates the plane of polarized light. Okay, so just a little bit more information about that slide there is that we have a photon, and the photon is propagating in a direction of space, and a photon is a kind of electromagnetic radiation, And it is called that because the photon is associated with an oscillating magnetic field and an oscillating electric field. And these two fields are perpendicular to each other. So you have the electric field is oscillating in up and down, maybe something like that. That's the electric field. And then you have the magnetic field, which is oscillating perpendicular to the electric field. That's the magnetic field. And if you just have a certain, just a random light bulb, so in that image saw a light bulb here, and the photons that are emanating from this light bulb, their electric fields are oscillating in just in random directions. So maybe one photon, its electric field is oscillating in the plane of the paper, but then you have another photon coming out of this light bulb, and its electric field is oscillating in a different direction, so that just a plain old ordinary light bulb, we have random E field oscillation. And so what the polarizer does, what this polarizer does is it admits only those photons whose electric field are oscillating in a given direction. So everything, all of the other photons are absorbed by the polarizer. Okay, so these guys now, we can say that after emerging from the polarizer is that the E fields, the electric fields, are all plane polarized. All of those other photons whose electric fields are oscillating in some other direction, they have been removed by the polarizer, and that's what enters that sample tube that I showed you, and that is what ends up, if we have a chiral molecule in here, I have a chiral molecule. The incident direction of oscillation was maybe up and down, but this chiral molecule is going to rotate the plane of polarized light by an angle alpha. Okay, so that's the setup. If the sample is a 50-50 mixture of two enantiomers, comma, the plane of polarized light will not be rotated. And this is because enantiomers rotate the plane by equal amounts, comma, but in opposite directions. So the plane polarized light enters the polarimeter. It meets, let's say, an R absolute configuration molecule, and so that the plane is rotated by a certain amount, and then that photon continues to move through the sample, and if it hits an S absolute configuration molecule, the plane of polarized light will be rotated by an equal amount, but in the opposite direction. So it's back to being straight up and down. And then that light beam continues to travel through that sample tubes, and it hits another S absolute configuration molecule, and it's rotated by a certain amount. And then it continues to travel through that sample tube, and it hits an R absolute configuration molecule, and the plane of polarized light is rotated back into the initial direction. So this is an important fact about this polarimetry experiment, that the enantiomers rotate plane polarized light by equal amounts, but in opposite directions. This 50-50 mixture of enantiomers, this is called a racemic mixture, or sometimes it's also referred to as a racemate. And when you run a reaction in the laboratory, lots of times you don't get the pure enantiomer. You get something that is a 50-50 mixture of two enantiomers. We talked about ibuprofen and thalidomide and salambuterol. Maybe you've heard of that. That's I believe that's an asthma medication. Those are racemic mixtures. They have 50% of the R enantiomer and 50% of the S enantiomer. They will not rotate the plane of polarized light. Nor do achiral molecules rotate the plane of polarized light. So it has to be the molecule has to be chiral, and the important fact here is that in order to observe that rotation, there has to be an excess of one enantiomer over the other in order to see the rotation of the plane of polarized light. If you have a 50-50 mixture, yes, that plane of polarized light is being rotated, but it's being rotated by equal amounts, but in opposite directions every time it encounters an enantiomer. So the overall effect is no rotation. And if the molecule isn't chiral, it doesn't interact with the electric field. Okay, some chiral molecules rotate the plane in the clockwise direction. These kinds of samples are said to be dextrorotary. Dextrorotary. So maybe you've heard of dextrose. Well, where did that name come from? Well, way back in the 1800s, one of the observations that was made about glucose, which is dextrose, one of the observations that was made about glucose is that it rotated the plane of polarized light in the clockwise direction. So it was named dextrose. But then we also have some molecules that rotate the plane of polarized light in the counterclockwise direction. And these samples are said to be levorotary. And so maybe you've heard of something called levulose. Levulose, once again, back in the 1800s when they were just figuring out the fundamental facts about chirality and the plane polarized light and all of that, there was a substance called levulose. It was a sugar, and it rotated the plane of polarized light in the counterclockwise direction. They didn't know what its structure was, but they named it levulose in order to communicate that it rotated the plane of polarized light in the counterclockwise direction. A dextrorotary sample is indicated by the symbol plus, and a levorotary sample is indicated by this designation of minus. And these are stereochemical descriptors, just like R and S and E and Z. So they would be way at the front of the name. There is no correlation between R and plus or minus, or between S and plus or minus. So I don't want you to think, well, an R absolute configuration chiral molecule rotates the plane of polarized light in the positive direction. No, some in the positive direction and some in the negative direction. And similarly for an S absolute configuration enantiomer, that rotation could be either positive or negative. So this is how we establish that we're looking at a chiral sample in the laboratory, this polarimetry experiment, this optical activity experiment. And when we get a negative result, it's either because the molecule is not chiral or we happen to have a 50-50 mixture of two enantiomers. Okay, so let's put this on a quantitative footing in that we can calculate the percentages of dextrorotary and levorotary enantiomers using this formula here. And you don't have to memorize this formula, but you do need to know how to work with it. 1 plus the observed rotation divided by the specific rotation of the pure enantiomer times 50%. Okay, so this is the formula that we can use to calculate the percentages of plus or minus in our sample. All right, so definition of the symbols here: alpha observed, this is the observed rotation, and alpha pure, this is the rotation of the pure enantiomer. Okay, so let's look at an example of this equation in action. So if I take this molecule here, all right, and it has a chirality center, and I react that with water, I get, this is a reaction we'll talk about later on in the term, I get two products here. I get this guy, which has the S absolute configuration, and I also get its enantiomer, which of course will have the R absolute configuration. Now, the specific rotation of this particular pure S enantiomer is positive 25 degrees, right? So that's the specific rotation of the pure S enantiomer. What is the specific rotation of the pure R enantiomer? Okay, tell me in the chat. What is the specific rotation of the pure R enantiomer? The pure S enantiomer is plus 25. What's the specific rotation of the pure R enantiomer? Anybody giving it a shot out there? Oh, it's going to be minus 25 degrees, right? Because enantiomers rotate the plane of polarized light by the same angle, but in opposite directions. So this is going to be minus 25 degrees. And notice again, just to repeat, because this is a constant source of confusion, is that plus does not mean S and minus does not mean S. There is no correlation between R and S and the sign or the direction of the rotation. Okay, so we did this experiment and we determined that the specific rotation of the mixture is 9 degrees. Okay, so before we do any calculations, before we slam that into this equation, tell me, is there more R or is there more S in the sample? So tell me in the chat. Pure S is plus 25, pure R is minus 25. The mixture that this reaction gives has a specific rotation, has an observed rotation of 9 degrees. Is there more R or is there more S in the sample? Well, there's going to be more S in the sample, right? Because if I had a 100% pure sample of S, it would be dextrorotary positive 25. That this is a positive number means there must be more S enantiomer in there. That's positive, there's more S enantiomer in the sample. Okay, so now finally I can slam this number into this equation, and I see that the percent of the dextrorotary plus is equal to 1 plus the specific rotation of the mixture, which is plus 9, divided by the specific rotation of the pure S, of the pure plus, right? This is plus because this is plus, times 50%, and I'm getting 68%. All right, and so what would be the calculation of the pure minus? That would be 1 plus the specific, the observed rotation of the mixture. And what is the specific rotation of the pure levorotary guy? Well, now into this number, I would put minus 25 degrees, right? I'm calculating the amount of levorotary guy, of minus guy. So the number that I'm putting into this equation for alpha pure will be the data for the minus guy, right? Okay, and so now this is going to work out to be 32%. All right, so this is well, how we can establish that we're looking at a sample that has more of one enantiomer in it than of the other. And so we must be looking at a sample of a molecule that is chiral. Okay, so let's look at another pretty picture here. Just practical application. All right, so this practical application is I talked about earlier, I talked about dextrose, and that dextrose is glucose. And so this is it turns out that grape juice is almost exclusively glucose and water. And so what this fellow is doing here is he is a wine grower, and he's taken a grape and he's crushed it up and he's sampling the grape juice, and that way he can calculate how much of this chiral compound D-glucose is in that grape juice. And so now he knows whether it's time to harvest the grapes and start making wine. So this is just an application of this polarimetry experiment. Okay, and so this slide here, it gives the full rundown of what sometimes you'll see in a systematic name for 2-bromobutane enantiomers. The R absolute configuration guy on the left, he's specific rotation of -23. So notice how the name is constructed. That minus in parentheses means it's levorotary. And then the R is telling you it's an R absolute configuration. There is no correlation between the sign of rotation and the absolute configuration. And then the other guy, the S enantiomer on the right-hand side of this image, that's the dextrorotary enantiomer. And so that plus means it's dextrorotary and it has the S absolute configuration. Okay, so with that out of the way, we can draw a heavy double line here. And that would be the end of the material for quiz number 3. Okay, but now I have a big, huge fish to fry, and that is nuclear magnetic resonance spectroscopy. And that's what we're going to be spending a couple of lectures talking about. And that's also what your lab on Thursday is going to be about, NMR. So we'll have a pre-lab lecture today, but I'm going to say a lot of, rather than just to repeat that pre-lab lecture, I'm going to say a lot of what you need to know in order to understand that lab and to work with that lab. All right, so our new topic, nuclear magnetic resonance. That takes an awful long time to say and write, so we just always abbreviate this NMR, nuclear magnetic resonance spectroscopy. This instrumental technique is the most important analytical technique in the organic chemistry laboratory. NMR, in fact, is the only thing we believe, really, when it comes right down to it, in the organic chemistry laboratory. We run a reaction, we've created a new substance, or we've isolated a substance from a natural source. Whether that sample is pure, what it is, this is the technique that is used. And what NMR tells the carbon skeleton of the molecule, it tells what the carbon skeleton is. So up to now, we've been very blithely writing the structures of this, that, and the other molecule, and we've been establishing that something has the R absolute configuration, or the S absolute configuration, or an E double bond, or a Z double bond, or whether something is cis dichlorocycle. We've made a lot of comment about the structure of molecules, but what we haven't mentioned at all is how do we know that something has an R absolute configuration, or how do we know that something has an E or Z double bond, or how do we know that something is cis dichlorocyclohexane and not trans dichlorocyclohexane? Well, this is how we know. NMR. This is what we use to determine the structure of molecules. Okay, so let me show you some stuff about NMR. Oh dear, that's wrong. Okay. Here we are. Okay, so NMR is used to figure out the structure of molecules. So this will be our goal in our study of NMR, to go from an NMR spectrum, that's what this is, a nuclear magnetic resonance spectrum, and we'll usually have the formula, not always, but frequently we will. We'll have the formula, we'll have the spectrum, and what we want to do is to be able to go from this information of the formula end of the spectrum to the structure, right? That's our goal in our study of NMR. We go from the spectrum to the, to the structure. So this is how we determine what the structure of a molecule is. NMR is a technique that we maybe, I'm sure that we've heard of just in daily life. This is the technology that is used in the magnetic resonance imaging, the MRI. Because what we're going to say about NMR shortly is that the proton, the hydrogen nucleus, produces a different NMR signal when it is in different chemical environments. So for example, the hydrogen nucleus in water produces a certain signal when it is inside your brain, which has where it's surrounded by a lot of fat. That's one chemical environment. And the hydrogen nucleus of water will produce a different signal when it is in the chemical environment surrounded by muscle. And it will produce a different signal when it is trapped in the chemical environment of a bone. And so all of these tiny little differences that are occasioned by the chemical environment which a water molecule finds itself in is exploited to produce these magnetic resonance images. So when you're looking at when you're looking at an MRI, what you are looking at is really an NMR. It's the same kind of technology. Okay. So let's talk first of all about the physical basis. Oh my gosh, all these pens are no good. Physical basis of the NMR. Okay, so what we're going to be doing is that some nuclei have a non-zero nuclear magnetic spin, right? And so spin is nothing new to us, right? In Gen Chem, we talked about the spin of the electron, and some electrons are spin up and some electrons are spin down. Well, nuclei also have spin, but this is associated with the magnetization of the nucleus. Now, the only nucleus we're going to be really focusing on is the proton. The proton, which is also called the hydrogen nucleus, right, has the nuclear spin equal to plus or minus 1/2. So this is just the quantum mechanical description of the spin of the proton. And so what this is saying is that some protons are spin up plus 1/2, or you could also represent that by an upward pointing arrow. And some protons are spin down minus 1/2, and that can also be represented by a downward pointing arrow. So there's nothing really new here because we saw that the electron has all of the same spin characteristics. And so the proton has nuclear spin. It can be spin up or spin down, plus 1/2 or minus 1/2, an up arrow or a down arrow. Okay. So we imagine a magnet. So this is kind of like a simple picture of a magnet. And the magnet has north pole and south pole. And by convention, the magnetic field emanating from the magnet is a vector quantity, and it is seen to be emerging from the north pole and headed to the south pole. Okay, so this is kind of just a simplistic picture of a powerful laboratory magnet. Well, how powerful? Well, the most powerful or the magnetic field that we're most used to is the magnetic field of the Earth. And maybe if you've taken geology, and maybe if you've taken electromagnetic, a course about electromagnetism in physics, maybe you know that the magnetic field of the Earth is about something like 10 to the minus 4 Tesla, right? Which is not 10 to the minus 4 Tesla, 10 to the minus 4 Gauss, which is the measure of magnetic field strength. Well, the magnets that are used in NMR are thousands, hundreds of thousands, millions of times more powerful than the magnetic field of the Earth. So this is a powerful magnetic field in a laboratory. Okay, so now if we have a proton, the protons align their magnetic spin either with the field, right? That's the up arrow, that's the plus 1/2, or opposed to the field, that's the down arrow, that's the minus 1/2. And in there's approximately a little more than 50% of the protons, right? This is a proton, so maybe I'll put an H here to symbolize that's the hydrogen nucleus. A little more than 50% of the protons align their spin with the external magnetic field, and a little less than 50% align their spin against the external magnetic field. The situation where the proton is aligned with the field, this is the lower energy situation. That's why there are more protons that align their spin with the field than against the field. So this is the lower energy situation here. That's the low energy situation. And this would be the higher energy situation. So there's a band gap. There's a difference in energy between the spin up state and the spin down state. And now if the sample is irradiated with electromagnetic radiation of the right frequency, what is going to happen is that the proton can be promoted. Though these protons that are in the lower energy state can be promoted to the higher energy state upon the irradiation of electromagnetic radiation, which is of this appropriate energy, and that would be something in the radio frequency range of the spectrum. So now you add RF, radio frequency radiation, and what happens is that you get promotion of the spin up protons to the spin down state. You get promotion of the electrons in the lower energy state to the higher energy state. So the RF, this is radio frequency electromagnetic radiation. And this promotes the spin up protons to the spin down state. So the protons are absorbing energy. They're going from the lower energy situation to the higher energy situation. Okay, so now let's put this, let's get a little bit quantitative with this, is that the amount of energy that is needed to bring about this promotion is equal to Planck's constant times the magnetic field strength felt at the proton. So H, that's Planck's constant. And this B sub P, that is the magnetic field experienced by the proton, needed to bring about promotion, right? That's the amount of B field, that's the amount of magnetic field that's needed to promote the spin up proton to the spin down proton. And for this situation that I've represented here, the magnetic field that is experienced by the proton is simply the magnetic field of the external laboratory magnet. Okay, so we're not really interested in an isolated proton, because this is the equation that holds if we're just looking at some isolated protons. But what we're really interested in are protons in organic molecules, where the proton is immersed in a sea of electrons, right? This is the situation for just a naked proton running around somewhere. But we're interested in protons that live in molecules. So we have to modify that equation a little bit, is that electrons surrounding protons in molecules produce a magnetic field of their own. And I'm going to call this B sub E, right? That's the magnetic field that is produced by electrons. And this magnetic field opposes B lab, right? And so maybe if you've taken courses on electromagnetic radiation, you know the right-hand rule and all of this other stuff. Well, this is just an expression of that. So let's go to another little simple little picture here. So there's our magnet. There's our laboratory magnet with the lines of force going from the North Pole to the South Pole. There's our lab magnet. And here's our proton. And now this proton is in a molecule. And so just going with this simple little planetary model of the atom here, right? There's the electron, and the electron, let's just say, is orbiting the nucleus. And this electron is producing a little magnetic field of its own, but that magnetic field is opposing the external magnetic field. So we can draw lines of force from this electron coming out like that, but see how the lab magnet, those arrows are pointing up. Here they're pointing down because the electron produces an opposing magnetic field. Okay, and so now putting this on a little bit more quantitative footing, delta E, that's the amount of energy, that's the amount of energy that the RF must have in order to bring about the promotion of the proton from the lower energy spin up state to the higher energy spin down state. Well, that's always going to be equal to Planck's constant times the field that is experienced by the proton. But now, because our proton is immersed in a sea of electrons, the proton is not only feeling the external magnetic field, but now it's also feeling the magnetic field due to the electrons in the molecule in which it is residing, and those electrons produce a magnetic field that opposes the lab field. So if the electrons weren't there, if the proton wasn't in a molecule, it would just feel B lab. But now it's in a molecule, it's feeling a little bit less magnetic field because the electrons are taking away. Okay, so now let's just rearrange this equation a little bit. B lab, right? This is the amount of laboratory magnetic field needed for promotion is going to equal delta E over Planck's constant, just doing some algebra with this equation here, plus BE. All right, so what this equation is telling you is that if the proton is in a molecule that has a lot of electron density around it, BE is going to be big. And if the proton is in an environment in which there's less electron density is going to mean less BE. So what this equation is saying is that lots of electron density, that's going to mean a big BE, and that's going to mean that we need a big laboratory field to bring about the promotion. Conversely, little electron density, that's going to mean that the BE is small. And that's going to mean that we need a small B lab to bring about the promotion. Okay, and so this is a very important concept of NMR, is that when the proton is in different chemical environments, when it's surrounded by more or less electron density, the laboratory magnetic field is going to have to be modified in order to bring about that promotion. Okay, so let's look at an NMR spectrometer here. Okay, so where is it? So here's a schematic of an NMR spectrometer. So there we have our magnet. And of course, it's not a bar magnet in the instrument. This is all done with electronics. The NMR instrument is extremely sophisticated, extremely complicated, and very, very expensive. So we have our sample immersed in the external magnetic field, and then we zap it with electromagnetic radiation in the radio frequency range. And if the energy of the electromagnetic radiation is right, we'll get this promotion of the spin up proton to the spin down state. And so what we see here is that this, the beam passes through the sample, and has a detector, and the detector knows how much RF was pumped into the sample, and it also has a way of detecting how much RF emerges from the sample. So if all of the RF that went in comes out, then promotion didn't happen. But if some of the RF that emerges from the sample, if some of it is missing, that means we must have gotten promotion of the proton from the spin up state to the spin down state. And by all of this electronic wizardry, that is turned into the NMR spectrum. Okay, so that's just the principles of operation, bare bones of how an NMR spectrometer works. Okay, so here's a 400 megahertz NMR spectrometer. The 400 megahertz, that is how the magnet is rated. So the magnetic field strength, we don't talk about Tesla or Gauss or anything like that. We use this unit of megahertz to denominate the magnetic field strength of the external magnet. And so this a metal cylinder here, that's where the magnet is, and the sample is inserted into this sample. And then the operator sits here, and this is all of the computer peripherals that are needed to control the experiment. And again, like we said before, you know, NMR is the technology of the magnetic resonance imaging, where what we're looking at is the proton in water. And when water is in different tissues, it's in different chemical environments, and it's going to produce a different signal. And so, you know, there's the bar magnet over here, and there's the sample, a human being. So let me ask you this. Anyone ever had an MRI? Tell me in the chat. Tell me if it was a pleasant experience or not. Anyone ever had an MRI? Not pleasant, was loud, yeah. Did you have to stay still? Did you have to lie perfectly still there for a long time? Yeah, and you know that that MRI that you sat still for 40 minutes in, do you know how much that cost the hospital? Just take a wild guess. Tell me here in the chat how much you think that MRI cost. Full body MRI. Thousands, not even close. How about $25 million with annual maintenance and operating expenses of $1 million? NMR is extremely expensive. It's extremely expensive technology for many reasons. One reason is that you're detecting tiny little differences in the magnetic field, and also you have all of the associated electronics. That's all very expensive. And then the magnet has to be chilled with liquid helium, which is also very expensive. Yeah, so MRI is an extremely expensive technique, but it is useful. Okay, so continuing to talk about physical basis of the NMR. All right, so when we look at an NMR spectrum, see something that looks like this. And the y-axis, this is the intensity. I can't write. Intensity of the absorption. And the x-axis, this is called the chemical shift. And the symbol of the chemical shift is the lowercase Greek letter delta. And the units of the chemical shift are the ppm, which means the parts per million. Okay, and the NMR chemical shift axis is kind of ass backwards because, you know, we want to see usually 0 over here and then 1 and then 2 and then 3 and so forth, but we don't get that with NMR. The 0 of the NMR axis is over here on the right, and the numbers we count up to 5, 10, 15, 20 ppm to the left. So the NMR chemical shift axis is kind of, you know, from right to left. Now, on an NMR spectrum, we never say right to left when we talk about NMR. What we always talk about is downfield. In other words, to the left, and upfield. In other words, to the right. But we never, this is how we indicate direction on the spectrum. And the reason that we use this vocabulary is because the B lab is increasing in this direction, right? Because when the proton is in a molecule, in order to bring about the promotion, we have to tune the B lab, because some protons need more magnetic field, some protons need less magnetic field, depending on how big BE is, right? We showed this little naive little picture, simple-minded picture about how the electron detracts from the external magnetic field. So that as BE increases, in order to bring about the spin flip, we need a bigger B lab. So that's why we call this upfield and downfield. The 0 of the NMR chemical shift axis, this is the location of the signal that is due to, this is the signal due to tetramethylsilane. So tetramethylsilane is a silicon atom bonded to 4 methyl groups, and this is abbreviated TMS. Okay, so let's see what would be happening in an NMR experiment. So I have my sample in my magnet, right? And I'm irradiating it with RF. And let's say I start with a low B lab. B lab is increasing this way. And so B lab isn't right. I'm looking at a proton. B lab isn't right. B lab isn't right yet. And now suddenly B lab has the right magnetic field to bring about the promotion. And so what we see is that the amount of RF that went in is now greater than the amount of RF that came out. And so what we see is a peak, right? So this baseline, this is correlated to the amount of RF that was shot into the sample, but now some of it is missing because some of that RF was absorbed, and that was picked up by the detector, and so we get a peak. And so maybe we get another peak over here like that. And then maybe we have some TMS in the sample, and we have a peak there. Okay, so we want to understand why it is that want to understand more why it is that we have some peaks that are to the left and some peaks are to the right. So let's make a little list of the NMR issues that we will entertain. Okay, first issue is the location of the peak. In other words, the chemical shift. Why are some peaks to the left and some peaks to the right? Why are some peaks upfield and some peaks are downfield? So that's an important issue. Another issue that we have to contend with is the number of peaks. Because if you look at tetramethylsilane structure here, so this is 3 times 4, this is 12 protons, but we don't see 12 peaks. We only see 1. We see 1 peak at 0 ppm. So why is that? If we're looking at 12 protons here, and remember we're only looking at proton spectroscopy, if we're looking at 12 protons here, why don't we see 12 peaks? Well, that's another issue. Why do we just see 1 peak? Another issue that we deal with will be the size of the peak. Some peaks are big, we'll see, and some peaks are small. Well, why is that? Why aren't they all the same size, or why aren't they random? And the fourth and final issue that we deal with is the splitting of the peak. So this doesn't mean too much right now, but it will eventually. Okay, so the location of the peak, the number of peaks, the size of the peaks, and the splitting of the peaks. So let's go back and let's look at an NMR spectrum and try to just get some. All right, so this molecule, that's this guy here, 1, 2, 3, 4. This is 1,3-dichlorobutane. And so we see that some peaks are upfield and some peaks are downfield. Well, why is that? Another thing is that we have 8 protons in the molecule. We see its formula there, 8 protons in the molecule, but we don't have 8 peaks. I don't know how many we have, but it's not 8. Why is that? Why doesn't every proton produce a peak? Some peaks are big and some peaks are smaller. Well, why is that? And furthermore, some peaks, this guy here, for example, the most upfield peak, it looks like we have 2 closely spaced components, but the next most downfield has 4 components, and then this one has 3, and this one has, it looks like 6. Well, why is that? And all of that's the splitting, and all of that is telling you some kind of information about the molecule under study. Okay, so it's time for my break. So my clock says 10:03. I'm going to go wet my whistle, and I will be back at 10:10. Okay, so first up, we're talking about the location of the peak, and the location of the peak. We have, first of all, the electronegativity effect. And this is saying that a proton close to an electronegative atom is experiencing a proton close to an electronegative atom is experiencing a small B small b lab, because the electronegative atom strips electron density away from the proton. So if a proton is close to an electronegative atom, such as chlorine or oxygen or something like that, that electronegative atom is sucking electron density away from the region of space where that proton is. And so in order to, and because the external magnetic field is being detracted from. So if the proton is close to an electronegative atom, the signal is going to be downfield. So this is the electronegativity effect. So let's look at an example here. Okay. See, electronegative atoms, they cause these downfield shifts. So on this slide here, we have where the NMR signal for methane would be. So carbon, so remember, we're looking at protons. We're looking at the environment that the proton is in. And carbon and hydrogen have very similar electronegativity. So there's very little stripping of electron density away from these hydrogen atoms by this oxygen. But now, as we start adding electronegative atom, for example, iodine, we see that the peak sails downfield from about, here is about maybe 0.2 to about 2.2. And why is that? Because the iodine atom is electronegative, and it is taking electron density away from the from those protons, and so the shift, the peak is further downfield. Now, when we increase the electronegativity, we go from iodine to bromine. The peak goes even further downfield. So here it is at around 2.7, right? And when we increase the electronegativity yet again, the peak has sailed down here to about 3.1. So what we're looking at are these protons on these molecules and how they are responding to being close to an electronegative atom. So that's the electronegativity effect. But the electronegativity effect is attenuated by distance, and it's also attenuated by the how electronegative that substituent is. So on this slide, what we see here is our the protons in chloromethane. So these protons are close to an electronegative chlorine. But now when we add a second electronegative atom, the peak goes even further downfield because there's more shielding, there's more stripping of electron density away from the proton. And when we add a third chlorine atom, the peak even goes further downfield to around 7 ppm. So the presence of this electronegative atom, well, that's also attenuated by how many electronegative atoms there are. And the effect is also attenuated by the distance of the proton from the electronegative atom, as illustrated in this slide here. So remember, we're looking at protons. So this is dimethyl ether. The protons in dimethyl ether are 2 bonds away from an electronegative oxygen. So see where their signal is, see where their peak is at around 3.3 ppm. Now, when we move that electronegative oxygen farther away, so in this ditert-butyl ether, now these protons are 1, 2, 3 bonds away from oxygen. Right, in this methyl ether, they were 2 bonds away from oxygen. Over here, they're 3 bonds away from oxygen. The peak is further upfield, so that the electronegativity effect, this is also depends on how far the electronegative atom is from the proton. Okay, so this electronegativity effect, important things to remember about that is that the effect depends on, first of all, how electronegative is the electronegative atom. How many electronegative atoms are present, and finally, how far the electronegative atom is from the proton under observation. Okay, so that's the electronegativity effect. If the proton is close to an electronegative atom, the signal is going to be downfield to the left. If there aren't any electronegative atoms, or if they're very far away, the signal is going to be upfield over here to the right. Okay, so let's do a little problem. So I'm going to draw the structure of a molecule here. And I'm going to call these protons A. I'm going to call this proton B. I'm going to call this proton C, D, and E. All right, and now over here, I'm going to list their chemical shifts. All right, 1.8, 2.0, 3.6, 4.1, and 5.8, right? So this is the chemical shift delta in units of ppm. Okay, so now let's match the proton to its chemical shift. Okay, so let's see. And I want you to try to respond to this here on the chat. All right, so the easiest one to identify, that's going to be the 5.8 guy, right? The most downfield signal, closest to the most electronegative atoms. Which proton is going to have this 5.8 chemical shift? Remember this, the chemical shift depends on how electronegative is the atom close to the proton, how many there are, and also the distance. So this 5.8 is going to be which one? Oh yeah, this is going to be E. No doubt about that. right? Because this proton is 2 bonds away from 2 chlorine atoms. Oh, chlorine's very electronegative. That is stripping all kinds of electron density away from this proton, making the signal downfield. And the E proton is also 3 bonds away from another chlorine atom. So yeah, E is the most downfield signal, no doubt about that. Okay, so how about let's try for the 1.8, right? So this one I think also might be easy. Which one is the 1.8 guy? That will be A, because the A protons are 1, 2, 3 bonds away from bromine. Bromine's is electronegative, but it's not as electronegative as chlorine. And most of these other protons are closer to chlorine. And also these protons are 3 bonds away from that electronegative atom. Okay, so now how about let's go for this 4.1. He's easy to spot as well. It's 4.1. Which proton is giving me this 4.1? Oh, that will be D. That will be D because the D proton is 2 bonds away from chlorine, right? This guy was 2 bonds away from 2 chlorine, so he's more downfield. It's 2 bonds away from 2 chlorine. Okay, so now what about this 3.6? Which one is he? Oh, that will be B because the B proton is 2 bonds away from bromine. So bromine is less electronegative than chlorine, so it makes total sense that the B proton would be upfield from the D proton because the D proton is the same distance away from a less electronegative atom. And I guess this narrowed this down that 2 must be C. So how'd that go? Well, I hope. Okay, so let's try again. Another structure, another matching problem. So I'm calling these guys A, B, C, and D. And the chemical shifts here will be 2.2, 3.3, 3.6, and 4.2. Okay, so let's match. Probably the easiest one is going to be the 2.2. Which one is the 2.2? Two 2.2 is going to be A, because see the D protons are 1, 2 bonds away from oxygen. The C protons are 1, 2 bonds away from oxygen. The D protons are 1, 2 bonds away from oxygen. The A protons are 1, 2, 3 bonds away from oxygen. So hope it makes sense that the A protons would be the most upfield. Okay, so now let's go for maybe this, probably this one, 4.2. Maybe this problem is a little bit more difficult than the one we just did, but let's try to match up the 4.2. Which one is he? Is it the B, the C, or the D? The 4.2 is which? Okay, I see some answers coming in. I like what I see. Yeah, the 4.2, that's the B proton. B, C, and D, they're all 2 bonds away from oxygen. But the B proton is 2 bonds away, is 1, 2, 3, 4 bonds away from a second oxygen on that side, and 1, 2, 3 bonds away from a second oxygen on the other side. So the B protons, they're simply closer to more electronegative atoms. Okay, so now between C and D, which one is C and which one is going to be D? This 3.3 guy is who? This 3.3 is what? 3.3 is D and the 3.6 is C. Okay, so there's the matching up. So how could we discriminate between C and D? Well, both the C protons and the D protons are 2 bonds away from oxygen, but the C protons are just closer to more electronegative atom on the left-hand side of the molecule than the D proton is. So the C proton is 2 bonds away from oxygen on one side and 1, 2, 3 bonds away from a second oxygen, whereas the D proton is 2 bonds away from oxygen, but 1, 2, 3, 4, 5, 6 bonds away from another oxygen. So I'm hoping that this kind of makes sense, this chemical shift effect. Okay, so now let's look at another spectrum. Whoops. Okay, so now here we see the NMR spectrum of methylbenzene or toluene. We see 2 peaks, and we see one of the peaks is at about 7 ppm. But if you look at the structure of this toluene, of this methylbenzene, I don't see no electronegative nothing anywhere. I don't see any fluorine, I don't see any chlorine, I don't see any oxygen, I don't see any electronegative atom anywhere at all. How is it that I could have a peak at 7 ppm? Okay, so an earlier example, so memorize that, 7 ppm. An earlier example that I showed you, here we have a proton that is close to 3 chlorines. It was also at 7 ppm. Well, that makes sense if you think about electronegativity, because this proton is so close to all of that electronegative chlorine. But in this spectrum of methylbenzene, there's no chlorine, there's no oxygen, there's no fluorine, there's no electronegative nothing. How could it be that that proton is so far downfield in the absence of electronegative groups? Well, that is because there is a second effect that is controlling the chemical shift, and that is diamagnetic anisotropy, or sometimes also called the ring current. So we have the electronegativity effect. We also have the effect, we also have the effect of diamagnetic anisotropy. Well, big word. Also called the ring current. Okay, and so what is happening there, so, you know, it's not just electronegativity all the time, there's also this effect of diamagnetic anisotropy. So once again, we go back to our simple-minded picture of our lab magnet. And now it turns out that pi electrons produce a magnetic field. I'm going to call that B sub pi, and that these reinforce B lab. And so we were looking at that picture of methylbenzene. And so we can imagine methylbenzene here. It has all of these pi electrons, and then we had a methyl group over here, and we have a proton there. And these pi electrons produce a magnetic field that reinforces B lab. In other words, we could draw these lines of force. Could draw these lines of force, but now these lines of force reinforce. See how the B lab arrow is pointing up? This B pi arrows are also pointing up. So that when we go back to this equation, delta E, that's the energy gap between the spin up and the spin down state, that's always going to be equal to Planck's constant times the magnetic field experienced at the proton. And so now the field that the proton is experiencing here is B lab minus B sub E. That's that detracting field that is caused by the regular electrons, the electrons that are not the pi electrons. And now the B lab is being helped out by B pi. And so rearranging this equation for B lab, this is telling us how much B lab we need to bring about the spin flip, to bring about the promotion of the spin up proton to the spin down state. Rearranging this equation, delta E divided by H plus BE minus B sub pi. Okay, and so this equation, just like an earlier one, is telling you lots of pi electrons. That means that B pi is big. That means that we need a small B lab. Conversely, few pi electrons, that means we're going to have a small B pi, and that means we need a big B lab. Downfield, upfield. And so in benzene, we have all of these pi electrons, and that is reinforcing, helping out the external magnetic field. And so that's why that chemical shift is so far down, even in the absence of any electronegative atom. So we have two effects going on here as far as the chemical shift is concerned. We have the electronegativity effect, and also this effect of diamagnetic anisotropy. Okay, so we've just taken care of how the factors that influence the location of the peak. Now let's talk about some of the factors that deal with the number of peaks. Right, that's our next NMR issue. Protons in different chemical environments produce different signals, produce signals at different values of delta, right? They are going to produce different signals at different chemical shifts. We just saw all of that, right? If the proton is close to an electronegative atom, if it's far away from an electronegative atom, if that atom isn't that electronegative, protons in different chemical environments produce different signals. The corollary of this is that protons in the same chemical environment these will produce the signal at the same chemical shift. And so how can protons be in the same chemical environment? There are two ways. Protons can be in the same environment in two different ways. First of all, by symmetry. So we're going to get to apply all of that stuff that we learned about the symmetry elements. Okay, what's going on here? Protons in different chemical environments produce signals at different values of delta, right? That's the symbol for the chemical shift. Right, is that what you were asking me? And the second way that protons can be in the same environment is by a rapid mechanism. That's much more complicated than by symmetry. So let's deal with protons that are in the same chemical environment by symmetry, first of all. Okay, so if protons can be protons that are related by a symmetry operation of the molecule. They inhabit are symmetry equivalent, comma, chemical shift equivalent, comma, and produce the same signal. Okay, so let's see, where are my models? All right, so looking here for my models. All right. Okay, so here's my little model. And we see that if we were to think about the symmetry elements of this molecule, does it have a center of symmetry, right? You see these white, does this molecule have a center of symmetry? No. Does it have a plane of symmetry? Yes, it does. It has a plane right here that says that the top of this molecule is the mirror image of the bottom of the molecule. So these two protons, these two white balls, which I'm taking to be the protons, they are related by a symmetry element of the molecule that they inhabit. They are symmetry equivalent and chemical shift equivalent, and they will produce the same signal. So even though this molecule, so this could be something like 1-chloro, 1-bromo, methane, even though this molecule has two protons, it's not going to produce two signals. It's going to produce only one signal because these two protons are symmetry equivalent. They are related by a symmetry element of the molecule that they live in. Okay, so this is what we're talking about. See this guy here? See this guy here? That is Fred. And see this guy over here? That's Mary. Okay, so that's Fred, that's Mary. Did you memorize where Fred is and where Mary is? So which one was Fred, and which one is Mary? Can't tell. You can't tell with certainty. Why? Because these two protons are symmetry equivalent. They are in exactly the same chemical environment and they will produce the same signal. Okay, so this is what we mean by symmetry equivalence. If two protons are related by symmetry, then they're going to produce the same signal. Okay, so let's do let's do some problems where we're probing this. I'm thinking of dibromobenzene. Dibromobenzene. There are 3 different dibromobenzene constitutional isomers. Draw them. Dibromobenzene. There are 3 different constitutional isomers that can be called dibromobenzene. First of all, let's draw them. Right, and remember, whenever we're talking about symmetry and benzene, it's best to use this Amit-Robinson formulation, not the alternating double and single bonds, because we know those aren't really double or single bonds. There are 3 dibromobenzenes. So the 2 bromines can either be next to each other like that, with 0 spacers in between, or there can be 1 spacer carbon in between, or there can be 2 spacer carbons in between. So there are the 3 possible dibromobenzenes. Did you get that part of the problem? One of these guys produces 1 NMR signal. One of these guys produces 2 NMR signals, and one of these guys produces 3 NMR signals. Which is which? 1 signal, 2 signals, and 3 signals. Which is which? Okay, so tell me in the chat here, which one produces 1 signal? Right here, here are the 3 dibromobenzenes. I'm going to call this one the 1,2 dibromo. I'm going to call this one the 1,3 dibromo. I'm going to call this one the 1,4 dibromo. So one of these guys produces 1 signal. Which one is it? Oh, it's going to be the 1,4. It's going to be the 1,4 that produces 1 signal. Why? Because of symmetry. Protons that are symmetry equivalent, protons that are related by a symmetry element of the molecule they live in, are symmetry equivalent, and they are chemical shift equivalent. So this guy has a plane of symmetry down the up and down plane of symmetry, and it also has another plane of symmetry left to right. So the one plane of symmetry is saying that circle proton is symmetry equivalent to circle proton, because this molecule has a plane of symmetry that says the top is the mirror image, symmetry equivalent to the bottom. And now the molecule also has a plane of symmetry that says the left is the mirror image of the right. So circle proton is symmetry equivalent to circle proton. All 4 of these protons are related by a symmetry element that of their molecule. So it's going to be 1 signal. Okay, which one of these guys produces 2 signals? Is it going to be the 1,2 or the 1,3? Which one produces 2 signals? So which one produces 2 signals? It's going to be the 1,2. The 1,2-dibromobenzene has a mirror plane of symmetry that says the top is the mirror image of the bottom. So that means that circle proton is symmetry equivalent to circle proton down there. But this molecule doesn't have a plane of symmetry that relates circle proton to square proton. Square proton and circle proton are in different chemical environments. They're going to produce different signals. Circle proton is 1, 2, 3 bonds away from bromine. Square proton isn't. Square proton and circle proton, they're in different chemical environments. They're going to produce different signals. This 1,2-dibromobenzene produces 2 signals. Right, so I saw a lot of people saying 1,4, 1,3. Okay, so 1,3, this is going to produce 3 signals. So this has a mirror plane of symmetry that says circle proton is symmetry equivalent to circle proton, but we have square proton up here, and he's not symmetry related to any other proton in the molecule. And then we have triangle proton down here, and he's not symmetry related to any other proton in the molecule. Square proton is tucked between 2 bromines. That's the only proton that can say that in that molecule, right? He's in a unique chemical environment that is not shared by any other proton. Triangle proton is tucked between 2 circle protons. Triangle proton is the only one that can say that. He's in a unique chemical environment not shared by any other proton in the molecule. But these 2 circle protons, they're in exactly the same chemical environment. Okay, so how'd that go? Ready for another one? Dichlorocyclopropane. Dichlorocyclopropane. There are 3 dichlorocyclopropanes. First of all, draw all 3 of them. One of them produces 1 signal, one of them produces 2 signals, and one of them produces 3 signals. Which is which? Dichlorocyclopropane. First of all, let's draw all 3 of them. Okay, dichlorocyclopropane. So there's my cyclopropane. I'm going to make this bond down here big and fat to show that it's closer to you. So I took that equilateral triangle and I'm just have reclined it. Dichlorocyclopropane. So there's my cyclopropane. All right, and there are 3 of them. One of them has both chlorines on carbon 1. I'm going to call this one the 1,1. The other one is the cis 1,2. And then the third and final dichlorocyclopropane is the trans. Okay, so there are the 3 dichlorocyclopropanes. There's actually 4 of them because this trans actually is chiral. So there are actually 2 trans dichlorocyclopropanes of the 2 enantiomers. Okay, and so once again, one of them produces 1 signal, One of them produces 2 signals, and one of them produces 3 signals. Which is which? Tell me in the chat. Which one produces 1 signal? Which of these guys produces 1 signal? Is it the 1-1? Is it the cis, or is it the trans? Okay, 1 signal, that's going to be the 1-1, right? We're looking at symmetry. And so the 1-1 has a plane of symmetry that says the left is the mirror image of the right. So circle proton is symmetry related to circle proton. But this molecule also has a second plane of symmetry that says the top is the mirror image of the bottom. So there's another plane of symmetry. I'm just going to dash it like that. There's another plane of symmetry that says the top is the mirror image of the bottom. So all 4 of these protons are symmetry related. They're in the same chemical environment. They're going to produce the same signal. Okay, which one produces 2 signals? The cis or the trans? So which one produces 2 signals? Which one produces 2 signals? The trans. And 3 signals, that's the cis. Whoops, looks like no one got it. Okay, so now let's look at the cis. So the cis has a plane of symmetry that says the left is the mirror image of the right. So circle proton is symmetry related to circle proton. But the molecule doesn't have a second plane of symmetry that says the top is the mirror image of the bottom. So we have square proton here, and we have triangle proton here, and they're in different chemical environments. They're not exchanged. They're not related by any symmetry element. Well, don't lose sight of the fact that what you're doing here is looking for chemical equivalence. Square proton looks to his left and to his right, and he sees chlorine. Triangle proton looks to his left and to his right. He doesn't see chlorine. He sees circle protons. Square proton and triangle proton are in different chemical environments. They're going to produce different signals. The trans stereoisomer, that produces 2 signals. What is the symmetry element? What is the one and only symmetry element of the trans? Somebody here tell me in the chat. The trans has only 1 symmetry element. What is it? Center of symmetry? Oh, no. The trans has a symmetry element. What is it? C3 axis went overboard there, too high. C1, everything has a C1. So it's not 1 and it's not 3, so what must it be? Yeah, the C2 axis of symmetry. It has a C2 axis of symmetry kind of like this, C2 that way. And so when I take the trans and rotate it 180 degrees, circle proton turns into circle proton. They are related by application of this symmetry element. And square proton, when I rotate this molecule 180 degrees, square proton up there up top turns into square proton down here down on the bottom. So the trans has two signals, and these two protons are exchanged. They are related by a C2 axis of symmetry. Okay, so let's see, let's just try one more. Trans 1,3-dichlorocyclobutane. Trans 1,3-dichlorocyclobutane. How many signals? Oh, sorry, not trans, cis. We could also do the trans, but let's do the cis. He's more fun. Cis 1,3-dichlorocyclobutane. Tell me in the chat, how many signals? So we're seeing here how a molecule can have a lot of protons, but it doesn't have the number of signals is ordinarily not the same as the number of protons, because protons in the same environment produce the same signal, and we can have, that's why the number of signals doesn't correspond to the number of protons. Cis 1,3-dichlorocyclobutane, how many signals? I'm getting 3. Okay, so try to give a drawing here. Big and fat bond here, that's in the front. Do I like the way I drew that? Maybe a diamond will be more instructive, right? Cis 1,3-dichloro. Ugly drawing. Okay, so the molecule has a plane of symmetry that says the front is the mirror image of the back. And it has another plane of symmetry that says the left is the mirror image of the right. So this proton is symmetry related to that proton by a plane of symmetry that says the left is the mirror image of the right. And this proton and this proton, they're related by that. This proton and this proton, they're related by that same symmetry operation that says that the back is the mirror image of the front, but square proton is not equivalent to circle proton. And then we have triangle proton down here, triangle proton down there. So we have three signals. Okay, so time is up.